Everyone. This week is going to be a pretty big week. We're going to be kind of doing three main things, all kind of regarding enemy logic and kind of more smart behavior from enemy AI and that stuff. So currently, I removed a lot of stuff, but currently right now we have enemies, the basic enemies up top, and they are doing nothing. And obviously, there is this issue where they fall through the platform. Um, I know the issue already, so what's happening is gravity is increasing, making velocity higher, so it skips the collision detection, because obviously if you're right here and you have a 2000 velocity, our current, how we do collisions is we just skip and we check over here, so it would pass through. So, but since we're doing enemy AI now, behavior trees and that stuff, we're just going to restart that from the beginning. So, I'd say the first place we should begin is looking at what I currently have. So for a basic enemy controller, I just have applying damage, and in basic enemy game object, I have the controller, polygon, collider, health, fading, hit, and rigid body with scale. So the first thing we need to do is we need to add this dot add component new behavior tree, and then the node is usually a new repeater, B2 repeater, and then we have to put in some sort of sequence or selector kind of in there. A lot of the stuff we have is actually relatively the same from my understanding from what we did in class. So we have a BT move right. And I should probably explain what I'm trying to do. There. What's going to happen is I want to use behavior trees rather than hard-coded if statements in order to make the enemy move left, hit this edge, move right, hit this edge. So we have to have some sort of BT move right, and we have to update the tree. We also have to have a move left, but we shall implement this. So first, one thing that I was having troubles with while implementing this is how to use the rigid body so we can have physics while using the behavioral tree. So one thing I kind of now do is I say RB equals tree.game object.get component rigid body. So I always get the rigid body, and then I usually, since they're constant, and I usually always get the enemy controller as well. Tree.game object.get component. Basic enemy controller. Okay, now we have the enemy controller and we have a rigid body. What we now need to do is we need to do rigid body dot velocity dot x equals, and since we're moving right, what we need to do is we need to do a positive speed for enemy controller, which in this case is 10. And then what we need to do is, since it was good, we need to return behavior tree dot success or succeed. It is the same thing with move left. The main difference is that it is a negative velocity. And we return succeed. Now we need to do class BT should move right. And now this is where we will differ from class. These obviously we're not trying to follow the player, we're trying to stick on the platform. So what we do is we get our constant enemy controller. And then what we need to do is we need some way to detect if we need to move right inside of our basic enemy controller. So I have a move right, which equals false. And let's build this out a little bit now. One thing you'll notice is that there will be nothing inside of update because all of our updates are now dealing with inside of the behavior tree. But what we want to do now is we want to do something where it's like, if we want to have some sort of platform, this is kind of a precautionary measure that I found, where sometimes it wasn't all the way on the ground, so we just have a velocity or a y velocity of 20 just to make sure it stays on the ground. Because we sometimes push up and then that causes it to fail. But what we need to do now is we need to say, hey, if the enemy bottom, which would be this bottom, is less than or equal to other top. So what's saying is that if the top of the other is below the bottom of the enemy, this enemy that we're attached to, we have to do something. Now there is the two kind of things we have to do where we have to say, hey, if we're moving in the positive direction, eh, or yeah, no, this works. So yeah, if we're moving in the positive direction or a negative direction, so we're moving left, and this left is less than or equal to other left. So what this is saying is that if your left is further than the other left, or lower or less than, which means it's further left, what we need to do is we need to call something here. It says reverse direction. Or I should say signal, we have to reverse direction. And then we do the same thing, but opposite. Where if it's greater than 0, and this right is greater than or equal to other right. One since this is kind of used in multiple places, I'm just going to make a new function called reverse direction. And what it's going to say is, hey, if you're currently if your x direction is positive, what we want to do is we just want to set this dot rigid body. Sorry, we want to do this dot move right. Movement right. Oh, sorry, movement right. And we want to set that equal to false. Because what's happening is you're moving positive direction, which means you're going right. And we say, hey, you don't need to move right anymore. Else, if this dot rigid body dot velocity dot x is less than 0, what we need to do is we need to set this equal to true, because what's happening now is that we will be moving right. And then we just do the simple actually no, yeah. Now what we do is now inside of here, we just call this dot reverse direction. And there is some redundancy here because obviously this dot rigid body dot velocity dot x, so we could just manually have it. So we could just do this where we go if it's at, we could do that, but what will happen is that we may need to add more stuff in there into the logic of reverse direction. So it's I'll keep it separated for now. Or you could also even just get rid of this as well. Um, so, but those are some small things. So now we have a way to reverse direction, and the way we reverse direction is based on the enemy controller's move right. Now, if we go back to the game object, we can actually see that should move right. Now we have a way to actually look at it. It's EC dot move right or movement right. And if it's movement right, then what we do is we return behavior tree of success or succeed. Otherwise, we return behavior tree dot fail. So what this is now going to do is it's saying, hey, if we should move right, we succeed. Otherwise, we fail. Same thing with move left. It is just the inverse, where it is move left. And then it should be not. So now let's kind of construct this. So how we should do something similar, move left sequence, where we do a new BT sequence, and that sequence should be new BT should move left, new BT move left. And the same thing for right. A lot of this is kind of a review, but we will be adding a little bit extra to it. After we kind of get this movement working. And then we just have a constant movement select. And then what we want to do is a BT selector. And inside of the selector, what we want to do is we want a move left sequence and then a move right sequence. And then inside of here, we do movement as our note. And we're get component. Did I misspell get component? A game object. Let's make sure. Oh, I misspelled game object. Game. I misspelled game object. And now let's see. Okay. Now it moves right, it moves left. But obviously that's still a little bit boring. Obviously there should be a little bit more to an enemy than just move left, even if it's basic. So what I will do is if I hit the enemy, it will sprint in the opposite direction of me. So, for example, what'll happen is it'll run, quote, run away from me. I'll hit it, and then rather than just going, it will go in the opposite direction and then run away. So let's kind of think about conceptually what we have to do. Well, first of all, we should have some sort of class B, like some sort of handle, handle, hit player, some way to handle how we actually hit the player. Um, and then we also kind of need some way to sprint. That would be class BT sprint. Um, but first, we need to kind of think logically about how we should do this in our controller. So obviously, we have the what was it? Oh yeah, we have the if we collide with the game object and the opacity of the game objects is 1, we apply damage, and we have this dot hit player equals true. So we already have a way of registering hit player. We just need some way to actually fully understand or like reverse the direction. So the way we could do this is with the math.sign. And what we want to do is we want to do other. We want to get the other component. We want to get their rigid body, and we want to get their dot velocity dot x. And if it doesn't equal math dot sign this dot rigid body dot velocity dot x. So then if we do that, what we want to do is we want to call reverse direction. So that so what this is going to do is say we are both moving in the positive direction. If I hit, we will now know that they can just speed up in the correct velocity. But if we are hitting each other head on, so one's moving left, the other's moving right, the enemy should move the other direction now in sprint. Um, and then there's kind of a weird secondary effect that is kind of hard to consider unless we play around with it a lot. But what happens if we hit up on the top of the enemy? Well, what's happening is it won't equal the same, and it'll just move back from forth, left and right, left and right. So the thing that we want to do is we just want to do a quick check as well of this bottom minus the other top or other bottom. And we just want to make sure that they're relatively close with each other. Um, ABS, there, there. Oh, math that sign doesn't have an end one. All right. So now what we have is when the component hits, we can reverse the direction now. And now let's update our game object. So with sprint, I think the sprint is the easiest one. What we do is we get the enemy controller, and we also get the rigid body. So we can actually just do this. And with the enemy controller and the rigid body, what we want is we want to do some sort of sprint speed. And let's say that equals speed times forward. Let's do 3 or 2. Some sort of constant. And we want direction equal to ec.moveRight. And what's going to happen is that if it's moved right, what we will want to do is set it equal to 1. Otherwise, it's -1. This is kind of just a condensed if statement. Then what we do is we simply do dot velocity dot x equals sprint speed times direction. And obviously, if we are sprinting, what we do is we return behavior tree dot succeed. With handle hit player, it's a little bit more complicated, but still relatively simple. Nothing too crazy yet. What's happening is if we hit the player, what we want to do is we just want to return behavior tree dot succeed. Otherwise, we return fail. So still relatively simple. If we hit the player, we succeed. Otherwise, we fail. And now it's kind of the hard part, in my opinion, of what should we do next. Well, first let's make the sprint sequence. So constant sprint sequence equals new BT parallel. And inside of the parallel, what we want is we want a new BT duration, and let's say of 1, and the new BT sprint. Now we have some sort of sprint sequence. Now we need some sort of handle hit. Handle hit sequence. And that'll be a new BT sequence. And what do we need to do? Well, we first need to see if BT handle hit player. And if you hit the player, then we call sprint sequence. So up here is the left-right movement. The sprints is the hitting the player and sprinting because of it. So now inside of movement select, all we need to do is we need to handle the hit sequence first. And then if that's not good, then we just move left and move right. So now if we check this out, they move normally. When I hit them, there is an error. Cannot read reading times for collision.js. Okay, that means that there is an issue with velocity. ec.speed.x. And when we hit, looks like the duration is not working. Let's double check that. Let's make it a little bit more obvious. Let's do 5. When I hit, yeah, it has been long enough. So there's something wrong with our duration, but I do like the how it is being handled. So we have a new BT parallel, new BT duration of 1, and BT sprint. Inside of sprint, instead of turn succeed, we turn running. Apologies. We return running because obviously you sprint for the duration of that. So we don't want to return succeed or failure. We just want to say it's running until the duration ends. The BT duration ends. Now if we hit it, Oh, let's reload just to make sure. It is still going indefinitely. The x equals spring times direction. On return behavior tree dot running. Oh, we never switched the handle hit player off. That's why. We do so we turn it to true, but we never turn it off. So when we hit the player, we turn that tag off, and now it should work. And now we go back. See, and now it stops. And say if we go into the opposite direction, it runs away on the other side. If we do, if I hit it from behind, it continues in that direction. Now we have a very unique type of enemy. Something that is now we can use those BT nodes and then kind of expand it on other enemies, which we will show. Now let's work on a different type of enemy. Let's do a shooting enemy that shoots like lobs at you. Oh, and I did forget one thing. Let's actually explain this first as well. So obviously, yeah, let's explain this first before we do that. So, what I'm currently doing is I have my mouse and I want to be able to shoot a projectile. So let's do that. Inside of our basic enemy controller, what I have is inside, or nope, not basic enemy. It is player controller. Okay. What I have is I have inside of my update a statement that does input dot buttons down this frame dot include 0. So if it includes your 0 button, what we do is we get the world space of your mouse by using the built-in camera 2-screen world space, which is this. You can pause to transcribe it if you need. And then we get the direction from player based on the world space. So we subtract the mouse world space with the current position. We use A tan2 to get the angle from the player. And then we get the offset by using cosine and sine, and then times that by the scale divided by 2. So what we're doing is we're starting from the center, we're adding, and we're trying to project it on a line to make it at the edge of the player, so it looks like we're actually shooting out from the player. This will make more sense when we actually look at kind of how it actually works, but we can kind of do this. So say, for example, I'm right here, and I do this top left corner. You see how it kind of shoots from that left side? That's what we're doing. If we're doing top, it looks like it's shooting from the top. The right side looks like we're shooting more from the right. Yeah, so that's kind of the idea behind this. And then we instantiate a throwable projectile game object, which if we just go to there, we don't have any thing in our controller, so that's why it's not doing anything. But our throwable projectile game object has a polygon, collider, rigid body, and then some sort of throwable projectile controller with the given angle and speed times 250, because we'll say that it's kind of needed. But we can remove that right now. Now if we go to our throwable projectile controller, we kind of need to think about how we do this. So we have some sort of angle and speed. First, let's just instantiate or projectile game object. Yeah, this. So first, let's get the rigid body component. GameObject.getComponent rigid body. And then we set the rigid body dot gravity dot y equal to 512. And then we set the this dot rigid body dot velocity dot x equal to, and then this dot rigid body dot velocity dot y equal to. When we look at it, we have to do math.cosine this dot angle. So obviously, velocity in x is the cosine times your speed. And then math.sine, or y is your math.sine of your angle times your speed. And then we always do the other dot get component dot, and we do the health pool. Controller sees they can take damage, and then we do the Elvis operator, we apply damage. And let's just say 10. Heavy hit. And then we do this dot game object dot destroy. So we destroy it when we hit inclusion. So now one thing we actually see that now is that if we go over here, Sniper, assess out. It is not liking get component. I'm gonna spell it again. Get component. Oh. Game object. Okay, so now we look at it. If we hit up, down, there. Yeah, it looks like it's doing good. So we can hit, but obviously it's a triangle and it looks like it's just staying there. It's not kind of how you would think you would actually kind of look like when you would actually do it. So what we actually can do is if we get the rigid body dot velocity dot x, and if it doesn't equal 0, or the other rigid body dot velocity dot x or dot y, and that doesn't equal 0, what we can actually do is we can use this dot transform. We can set the rotation equal to the math dot a tan 2 of the y, the rigid body, the velocity of the y, and then the rigid body velocity of the x. And then when we look at it, and we actually see it still doesn't. I'm spelling again. Now you actually look at it and it actually rotates a little bit. And if we shoot short, if our mouse is here and we shoot, it's a little bit further, and it goes a little bit further every time. So if we go all the way up here and we shoot, let's try it and hit. And it takes the 10 damage. And then obviously you could adjust the speed always. But now you can actually kind of interact with your mouse, shoot. It collides with everything. Now here comes the fun part. What if we want an enemy to shoot at you? Now this is a little bit more complicated. So complicated in fact that I haven't tried to do a behavior tree of it, but I know it's possible. It's just constraints. So we won't use the behavior tree for this, but what I will do is we will use the just a regular component, and then we'll go through that. And then I can explain how I would think of doing a behavior tree of this. But what we want to do is we want to use this projectile enemy game object. So let's go to that. What we have is the polygon, collider, health pool controller, fading controller, hit effect controller, and then the projectile enemy controller. So now if we go to our projectile enemy controller, this is what we have. What we want to do is we want to say, hey, if we're within some radius of the enemy, we shoot. First, though, we have to set up the cooldown, and we always add time.delta time to it. And then let's begin on this. So let's say let diff. So first we need to get the difference between the player and our current enemy. So we do this dot player game object dot transform dot position dot minus this dot transform dot position, and then I throw dot clone on there just because I want to make sure everything's good. And then we get the opacity just because I can fade player game object dot get component polygon dot opacity. This is if you have opacity and you change it to fade out. If you don't, then you don't need it. But we do diff and opacity equals 1. So basically, if you get the difference, then you are good. So if the this basically saying if the difference exists. So if there's a player game object, so now what we need to do is we need to do the distance formula. So we do math dot s square root. We want to do diff dot x squared, diff dot x squared plus diff dot y squared, and we want to set c if that is less than this dot fire radius. And then we also need to make sure that the this dot current time is greater than this dot next shot time. So what this does is obviously we use the distance formula and we say, hey, if that's less than our fire radius. So if we're within distance of our fire radius, what we want to now do is we want to set this dot current time equals 0. This, or let's do let angle and radians equals math dot a tan 2. And we do the same thing of diff dot y diff dot x. We then do let offset x equal math dot cosine angle radians times this dot transform dot scale dot x. And then we do offset y sine y. And now what we do is now we instantiate again, similar to what we have done, or I showed you in the previous one. We now have the enemy throwable projectile game object. We want a new vector 2 for a position where we do this dot transform dot position dot x plus offset x. This dot transform dot position dot y plus offset y. Now, if we look at our enemy throwable projectile game object, we just have the controller, polygon, collider, rigid body. So if we look at the controller, though, there's nothing in there except some functions that I have just to remind me of how it works. But now if we go there, Obviously, what's happening now is it should spawn every 3 seconds a projectile, and if I go above, it spawns above. But yep, now that looks relatively good. Now we need to work on the projectile controller. How do we actually do it? Now, this is kind of what took me most of the time last week and why there is no weekly video, but I will try my best to explain this. So yeah, this dot rigid body equals this dot game object dot get component. So obviously we get the rigid body component, and then we need to get the player equal game object dot find player game object. Okay, now we need to get the base position. But obviously what could happen is that the player game object might not exist because it's dead. So let's do base position equal player game object. Tell this operator transform dot position. Now we do a simple if statement of base position. So if base position exists, what we will do is we will call, let's do compute launch angles. This dot compute launch angles. With our compute launch angles, what we will do is we will provide the base position and a velocity of initial speed. But what should this be? So there's kind of a couple of things we need to first establish. We want to get the dx, so the target position dot x minus this dot transform position dot x. We want to get the absolute dx. Math.abs dx. We also want to get the dy, which is just the same as the dx, but for y's. We want the constant gravity, which is 512. And then we need some vectors. So v2 will equal v times v. And then v to the fourth will equal v2 times v2. So this is just v to the power of 4 and v to the power of 2. What we first need to do is calculate d. Well, first, what is it? Well, what we're going to do is we are going to take the trajectory equation, which I will. And what we will do is we will manipulate this function to be a parabolic equation, which is something as x squared plus or x squared plus some or constant x squared plus constant x plus constant equals 0. And obviously with quadratic equations, we can do the negative b plus or minus the square root of 4ac or b squared minus 4ac all over 2a. And that square root is what we call the discriminant. And that's what we will be calculating first. And this is a very powerful tool for us because what will happen is if the discriminant is greater than 0, then there's two values possible because the square root means that there's a plus option and a minus option for doing it. If it's less than 0, then that means we cannot hit our player, which means that it cannot fire. So with this, what we can do is Obviously we have the trajectory equation, and what I will do, so first we'll try and simplify it. We obviously know cosine square, or not obvious, um, but what we do know is that cosine squared theta can equal 1 over 1 plus tangent theta squared. So what we can do is we can rewrite this equation and replace your dx or your y and x with dx dy to be more something like this, where you have dy equals dx. Actually, oh yeah, and let's actually do this as well, just to simplify it. What we will then be doing is we will then be using our tangent as our x value, so obviously inside of Desmos. If we have an x squared plus x plus 1 equals 0, or x, we have the parabolic equation. In this case, our x value, our x is going to equal tangent of theta, or tangent of x theta. And this is how we will be doing it, and so that we can actually determine the angle that we should use. Because what we can do is we can solve for x and then do the tangent inverse of it, and then we should get a theta that works. And so that's like the big picture. So the way we will simplify what we will do is we will have some sort of the difference in y equals dx times t, which in this case will be our tangent of theta. So let's t equals tangent of theta. And what t would then equal is, and we would subtract, and then it would be your g times your dx squared. And you would divide that by your 2v squared. And then you would times that by your 1 plus t squared. Because when we look at it, if cosine squared equals 1 over tangent squared, if we inverse it, what we'll do is then the tangent squared will be inside of the numerator, and we would get rid of this cosine. So that's what we kind of have done. Now what we basically have is we have this top function of. Now we have the denominator of 2v squared. And what we do is if we multiply both sides by 2v squared, or multiply it by 2v squared, what will happen now is that we will have an actual very nice equation. And another clarifying thing is we have to move the dy over as well. So what will happen is we will have 0 equals dx times t minus, actually let's do it this way. Let's do the an actual, so we have the dx squared because we'll times that by t squared, because that's what this means. We're multiplying the dx squared times the 1 plus t. So we have the dx squared t times t squared. Then we have the minus 2v squared dx with the t. So this is our x squared constant. So our a would equal that. Our b would equal this. And then our c, which is our constant, would be the d times dx squared plus 2v squared dy. Because what happened is then we subtracted the dy over. And if you don't understand this, what we're doing is we're just simplifying it a little bit. But we're just simplifying it. It is kind of complicated. I'm just trying to the best to make sure that there's at least a general understanding. But what we can do now is we could simplify this. So we have a t squared t and then no t equals 0. That's the quadratic formula of, so we could set a equal to our dx squared, our b equal to our negative 2 dx, and then our c equal to your this. So then what we could literally do is rewrite the equation of a t squared plus b t plus c. And obviously this looks like more of a quadratic equation than what we do. So how we calculate the discriminant? So the discriminant, d equals b squared minus 4ac. And then there's some ways to simplify this. But what we can do now is we actually can now know the discriminant, which is just this equation. And so we do 4 times dx squared times that by our v4 minus g, and times that by the parentheses of g times dx squared plus 2 times v2 times negative dy. This is the discriminant that we have. And this is the a way of just simplifying it for the most part. There's really kind of no tips or tricks. You just plug your A, B, and C in, and then you square it and simplify it. But what we can now do is we can actually use the discriminant now to say if D is less than 0. What we do is we return false because there's no way we can shoot because there's no solution that would hit the target. And now let's just do the square root, square root d equals math dot square root d. And now what we can actually do now is we can now solve our quadratic equation. Obviously, we can use the quadratic equation, negative b plus or minus the square root of d all over 2a. So one thing we can actually visualize this a little bit better if I write down. So what we want to do is we want to solve for t, which equals our tangent of theta. And then that equals negative b plus or minus the square root of d all over 2a. And it's hard to kind of understand all this. Again, just try and get the big picture. But what we can do now is there's 2 solutions we can do. We can do a lob shot. Well, let's not go there yet. What we have to do then is now we want to get the theta, which means that we would have to, in order for theta to equal, and then it would be inverse. We would use then a tan 2 of this equation that we have. And what that will do then is it will give us the theta that we can use to shoot. But obviously there's two things we can do. We can either add it or subtract it. What adding does, or the addition form, gives us a lob where it's from 45 to 90 degrees. Subtraction form gives a direct shot where it's from 0 to 45 degrees. So if you wanted a more lob shot, which I want because obviously there's differing y values, then what we will do is we'll use the addition form. So let's do that. We have to get the theta equal math dot a tan 2. And we want to do is negative b, which in this case is negative 2, times v squared times that by the absolute value of dx. So the one issue that took a lot of time for me to understand was that when do I use the absolute value when negative? Because one thing that sucks about the trajectory equation is it's not bidirectional. So this just was a lot of experimenting um, and stuff like that. But then obviously we already have the discriminant because we have the d. We calculated the d right there, and then we did the square root of it, so we can do that right there. And then we just need 2 times gravity times the abs of dx squared. Now we have a theta, and we can now just do this dot angle equals theta. And now we do this dot x speed equals v times math dot cosine of theta times that by math dot sine of dx. So we always did the absolute values inside of their theta and pretty much everywhere else except a few places. But we want to use, but what's happening is we're losing that sine value when doing the theta. So we just tack on whatever the sine of our dx is. That's where we do the, that's the direction we go in. And then for y speed, it is the same thing, but it is negative because what we're doing is we're going downwards instead of upwards. That was another issue that I had because it was shooting in the opposite direction. And what happened was is that in regular math, obviously, upper you go, the higher the y. In this case, that's not true for us. So we have to inverse it, or sorry, multiply by a -1. Now when we do the compute launch angles, we get some value. Let's just say let hit equal this. If hit, and this will be reworked even more, but say we hit, what we then want to do is, so say if we don't hit, we just want to this dot game object dot destroy. It can't hit, so why don't spawn it. But if it can hit, what we want to do is we want to set this dot rigid body dot velocity dot x equal to this dot x speed, and set the y velocity to y speed. Now, probably will go wrong, just because there's a lot there and it's hard to test unless it just works. So we will see. Yeah, as you can see, it's shooting way too far. So let's decrease the speed. Projectile, enemy throwing projectile. Let's do initial speed of 200. And we'll see that. $300. Okay, looks like the Y value isn't working. Looks like the X value is relatively correct. So let's go back and check. Velocity times math dot sine of theta. Let me double check everything. So then that is target position minus X minus position dot Y. Minus the start transform the position dot Y. Gravity is 512 V squared. Yeah. 4 times dx squared times v4 minus g times that by gravity times that by dx squared plus 2 times v squared times negative ty. Negative, parenthesis, negative 2 times velocity squared times that by absolute value of unit plus square root of b 2 times g times absolute value dx. This dot angle, let theta. Is it because of gravity? Do I even have gravity? I do not. That's why. I think it's because we have no gravity. That looks like it works. Obviously, it needs to be destroyed when it hits something, so let's just do a quick update on that. Let's just do the get component, health, pool controller, list operator, apply image 10. Let's do 2 so that we don't get one shot. But as you can see, and then this dot game object dot destroy. And let's see if it actually hits us up here. Oh, so as you can see, the speed is a very big issue. But it hits us now. So if we go up here, can't hit us, so it destroys it. So so what can we do about it? Well, there's a few things we are. There's let me actually do this as well. Projectile, let me controller. Let me go to the projectile. And let me also do this as well so it doesn't fall through the floor. It's something to our other, whereas if it's other.name equals platform game object, this dot rigid body dot velocity dot y equals 20, just so we stay on the ground. Constant opacity equals this dot game object dot get component polygon dot opacity if other dot name equals player name object and opacity equals 1. We do other dot get component health pool controller dot 1. Okay. Now it should stay on the floor, or yeah, it should stay where it should be. But obviously we have the issue of it not of speed. So it's like, okay, what if we increase our speed to something really high? I mean, that makes sense. I mean, obviously, if it's not always hitting inside of a radius, we want we want to launch it. So let's do like 800. Let's double it. Well, what happens is that then it kind of screws with now we're launching it all the way up here to hit that one enemy. But no matter where we go now, this should be able to hit. That's a good sign. I don't understand why it. Um, that's the throwable projectile controller, projectile enemy. Is weird. Because inside of main scene, we just do the projectile enemy game object that has that gravity by 12. What we'll do just temporarily, set this equal to 0, set gravity.y equal to 0. Since it won't be moving, I don't fully understand. But we still have it hitting. I do not know. But let's resolve the speed thing first, and let's see then afterwards. What could that be? So obviously we kind of need a way to adjust the speed. So let's start at 625. And one way we can do this is run through a for loop and simulate it multiple times to see if we hit the person. And if we hit, then we continue. So now what we will do is we'll say, hey, let low equal 0. Let high equal to something super high that won't really ever happen. And let velocity equal 0. What we'll do is we'll do a for loop where we say let I equal 0. I is less than 12, so we will do 12 iterations to refine this. And we'll do I plus plus. Inside of this, what we'll do is we'll say, hey, velocity equals I plus low divided by 2. So we'll average it out. Then we'll say, hey, can we hit? Equal this dot compute launch angles of the target position and some sort of velocity. If we can hit, what does that mean? Well, obviously that means at the very least, high velocity, this is our new high velocity that we can do. And what this means, or what it's doing, is it's narrowing down the range of where we can hit at. And then what we'll do next is if we can't hit, low equals this velocity. And what this will do is say we have to have a velocity of 500, between 500 and 600 in order to hit. What we'll do is we'll launch the 2000 and say, hey, we can't hit, or we need at least 500 velocity to hit. And if we hit 500 velocity, it is a perfect arc. What we'll do is say, hey, we'll start with 2000. Oh, we hit. or sorry, we calculate velocity by doing high plus low divided by 2, which will be 1,000. It'll say, hey, we hit, so let's reset the high equal to 1,000. Now we say, hey, does 500 or 500 hit? Because now our high is 1,000, our low is still 0. 1,000 plus 0 divided by 2 is 500. We see 500 can hit. Now we try again. Now we do with a low of 0 and high of 500. We say, hey, does 250 hit? Well, if 250 doesn't hit, what we'll do is say, hey, low equals 250. So now we have a range between 250 and 500. Now at the very end, what we do is then we say, hey, if we compute the launch angle of our target position based off of our high velocity, which hits, then that's kind of the, after searching for a while, that's kind of the lowest kind of thing we can do to hit. Now, if we implement this inside of here, instead of this, what we do is if we say, hey, yeah, let's do this dot compute minimum velocity to hit. Player position, or oh, sorry, base position. And if we do that, then we say, hey, we usually can fire. So then what we do is we then this say, so this dot rigid body dot x or dot velocity dot x equals this dot x speed. This dot rigid body dot velocity dot y equals this dot y speed. If the base position doesn't hit, we do else this dot game object dot destroy. Okay, so now if we look at it and we try, that speed is always trying to hit that little edge of a very nice arc. So if we go up here, it launches it all the way up there. And then, yeah. So now we actually have a relatively good arc. Now what we can do now is, just like our throwable projectiles, we can copy and paste this to make it look more like it's an arc. And then, yeah, I think that does it. So now you can, if you spawn, for example, say you wanted to throw a ball at an enemy, or an enemy throws a ball at an enemy, you can use this arc. Or if you, example, if you wanted to use the other form of a more direct line shot, as stated earlier, we could do subtraction. And what you do is you would subtract this, and it would be more of a direct line shot. So I can actually show. If we, or if you did a previous implementation of doing, I'll just do this. Compute launch angle. You do this, compute launch angle, base position, comma 625, and then we do subtraction. You'll see that it more is a direct hit. Well, that's the other option. But I don't want to do that option. I want it to be more of a lob, as stated earlier, because of. But another thing we can actually take into account is, hey, I don't want this enemy to be 100% perfect every single time. But what we can do is we can do like a radius equals 0, and then we do the angle equals math.random times math.pi times that by 2. So we randomize some sort of pi value, and we calculate distance. equal math.random times that by the scatter radius. And we could do a player position equals a new vector 2, where we do your base position dot x plus your math dot cosine of your angle times distance. And we can do the same thing for your y, which is y sine angle times distance. And then inside of here, instead of doing base position, you do player position. And that will give you some adjustment. So say I set this equal to 40. What you'll see is that it's not perfect now. So if I go right there, still hits, but you'll see it's slightly different. We can make this extreme and do scatter radius of 80, and hopefully, see how now that just straight up missed, and then that just straight up overshot. So then you can play with kind of this radius of where they kind of can miss and hit, and then go from there. Finally, we want one final enemy. Obviously, what's happening is that this behavioral AI can be complicated, so I wanted to make a more complex enemy where it hangs on the wall or like a top of a ceiling, and when it drops down to attack. So I will show you the enemy that we have, and I will comment this out just to make sure that. So obviously, if you saw the start, it starts up on a wall or the ceiling, and then it drops immediately, just because there's no logic behind it. So let's look at it. Falling enemy game object. What we have is the falling enemy controller, polygon, collider, that type of stuff, like normal. What we want to do is we need to create some sort of behavioral tree, and we also need to do the falling enemy controller logic as well. So let's start with the very basic falling enemy controller logic. So obviously hitting the player, that mostly makes sense. But let's actually do the behavior tree first, because that I think will make a lot of sense. There's kind of two things we need to actually look into. We need some way to see if we are above the player. We need to see some way somehow to drop the player. And one type of thing that I wanted to kind of really do to make it a little bit more is that when you drop on the player, you chase it until you hit an edge of the floor. So we'll have a class B T base player. And that'll be an update, and there'll be a tree. So first, we need some way to detect if we are above the player. So we do some sort of constant, and then me equals tree.gameObject. We need our rigid body equals enemy dot enemy dot get component rigid body, and then we need the constant enemy controller equals enemy dot get component falling enemy game object. As you can see in our controller, I already have the variables created. What we want is we want a has dropped variable, and a is chasing variable, a hit player variable, and a move right variable, because we already have a move left, move right. So we'll have to adjust that ever so slightly to accommodate for another enemy, but it'll make sense. what we want to do now is we want to say, hey, obviously, if there's no player or you already have dropped, we don't need to drop anymore. So what we need to do, actually, we don't need this. We need to get the player. Equals game object dot find player game object. So if we don't have a player or it's already dropped, we don't need to do it anymore. If we do have that, what we need to do is we need to do calculate the dx enemy.transform.position.x minus player.transform.position.x. And then we want some sort of tolerance, x. And let's set that equal to 20. So if it's 20 pixels apart, boom. And then we want to do if the dx is less than or equal to tolerance x, and the player.transform.position.y is greater than the enemy.transform.position.y. And we just want to make sure that it's also below the player. So that means if we go above it, then we don't want it to fall. And then what we do is we return behavior tree.succeed. If none of this happens, well, then we just return behavior tree.running. So now this is basically just a flag where it says, hey, we continuously do this. And then if it does happen, then we succeed, which then should let us go to the next one. So now inside of on drop player, what we need is we need this, and then we also need the rigid body. Enemy.get component rigid body. And what should happen? Well, if we are at this point already, that means that we should assume that we need to drop, and then we also need to do is chasing equal to true as well, so that we are now chasing the person, and then we also need to adjust the gravity dot y equal to 512, and then rb dot gravity or velocity dot y, and that's just give it a little boost at the beginning, and then return behavior tree dot succeed. So what we're going to do is that if we ever get to the drop on player, we just drop on the player. And then if this never happens, then it's we just won't ever come to this. So now let's kind of implement some logic. We want to use actually we already have a good idea of basic enemy game object of a move left and move right sequence. So let's reuse this. One major issue you may think of is, hey, in our move left, move right sequence, we get only the basic enemy controller, not the falling enemy controller, and that is correct. One better solution you could always do is have a enemy controller parent and then have children and then just get the component that is the child of it. But I don't want to do that. I am already doing a lot this video, so I will do this and say, hey, get the basic enemy controller. If that doesn't exist, what this double question marks means is that we try and get this instead. So everywhere I see an enemy controller, I will if I do tree.game object.get component basic, wherever that happens, I will just do this. Except sprint, because we won't be sprinting, but that's a different thing. So now we can use falling enemy game object.js, because now we just have added the falling enemy controller, which has all the variables. And now what we can do is now we can do the move left and move right sequence. And now let's kind of do the other sequences now. We want some sort of base movement. And base movement is just a new BT selector of the move left and move right. So we'll select one of those two whenever we want a base movement. Now, what we need now to do is we need to do a constant drop-down attack. And that is a new BT sequence where we do a new BT above player. And if you are now, then if that returns true, then you go into the BT drop on player. And now we have kind of two, now we have a new on ceiling movement. New BT parallel. And what we want to do now is for our ceiling movement, we want to parallel the drop down attack and base movement. So that means that it will be looking to do the drop down attack first. And if you don't, and then it'll also be doing the base movement as well. Now if we do and we also want to do it on floor movement, where we do a new BT selector, and we will either select between the new BT chase layer or the base movement. And then we just add component, new behavior tree, where the node is a new BT repeater movement. And then we need the constant movement, which is just a BT selector of first we check on ceiling movement, and then we check floor movement. Final thing we need to do is BT chase player. What we need is this, and then we also need the ridge body, and we also need the player. At least I think. Okay. What we're going to do is we're going to say, hey, if there's no player now, or you have not been dropped, return behavior tree dot failed. Because obviously then that means you've dropped and there's a reason, it's some weird reason. If you're also not dot is chasing, then there's also another error where we have to return a behavior tree dot failed. Because obviously you should be chasing at this point. And now we just do a constant enemy x equals enemy.transform.position.x. And then we do the same thing for enemy y, or sorry, player y, or x, player. And now here's kind of the one way I found to make it a little bit easier to move left and right. We have some sort of direction. If player x is greater than enemy x, then what we do is we want to do 1. If it's not, then it's -1. So if this is true, we'll use 1. If this is false, we'll use -1. And then now what we do is we just do rb dot velocity dot x equals direction times, let's say a speed of 70. And we return behavior tree dot running. Now we've established chase. Now let's do the controller, which is slightly more confusing. But so if we hit the platform, we want to actually check if we haven't dropped yet. So if we hit a platform, we want to be like, hey, if we haven't dropped yet, what we need to do is we need to reset your rigid body dot velocity dot y equal to 0, and this dot rigid body dot velocity dot or gravity y equals 0, so it actually hangs on the wall. Otherwise, it would just fall. If we have dropped, we just then set this dot rigid body dot gravity dot y equal to 512. This is where advanced collision handling would be good. Like collision on enter actually happens once, collision on stay happens every frame, that type of stuff. But this is just a good kind of setback. Or this is kind of just optimization thing. But obviously, what will happen is if our bottom is above the other top. So if we actually if we are now on top of the platform, we want to actually reset this dot rigid body dot velocity dot y back equal to 0, so that you don't fall through the floor. Now we need some sort of way to determine if we hit the left edge or right edge. So if this dot left or this left is less than or equal to other left, else if this right is greater than or equal to other right. Similar to what we have earlier, because obviously we're still using the movement as earlier as well. So it would make sense that it would also make sense that it's kind of similar. Well, we will also have a reverse direction, but in this case we will have a movement direction equals not this dot movement, move right. And what we'll do is we'll just say, hey, this dot move right will equal movement direction. Constant rigid body equals, well, we don't need to do that. Then what we can do is just do rigid body dot velocity dot x equals this dot move right. And if it does, it equals the speed, which we could say is 10, or it is -10. That's kind of a more optimized way of doing reverse direction. But obviously, if we're going left, what will happen is that this dot reverse direction will be true because now we're going to go right. And then it's false otherwise. And then we also need if this dot is chasing. So if we're chasing, what we need to do is we need to set this dot is chasing equal to false. Because if it is chasing and then it hits the edge, it should be like, okay, now I can't chase anymore because I can't go up over the ledge. Finally, there's a little bit for here. I mean, if capacity equals 1, other dot apply damage. Other thing we want to do is we want something similar to this, where we do the if. Let's go back to our basic enemy. This. Or if it's just a different sign, then we reverse direction. And finally, we also have to do this dot hit player equals true if it does hit the player. just to keep track of everything. So now hopefully, what did I use the wrong? Why does it not? It has 939. Hmm. Game object get component. I wonder why that. Oh, that's falling enemy game object. We need falling enemy controller and all these. Let's do a quick check on basic enemy game objects as well that I didn't. Okay, yep, that's the controller. Okay. And now it's moving super slow. If I walk over, hopefully it drops, chases the player. Let's see if yep, it chases the player. If we go over here and we hang on this wall, once it reaches the edge, it now should de-aggro, and then boom. There you go. Obviously, there's so much more you can do with this. And obviously, there's still a couple bugs here and there with some stuff. But I think this will give you a good kind of way of kind of tackling this kind of hard topic that it took me a while to even start to understand. Hopefully, you have a great rest of your day. If you have any questions, comments, or concerns, you can always ask after class or through email. Yeah.